Starting from this video, we're going to introduce how to program multiple GPUs. In general, there are three methods: stream-based, thread-based, and MPI-based. We start from the simplest one, the stream-based multi-GPU programming. So the purpose of multi-GPU programming is to allow those GPUs to run workloads concurrently. And we want to find existing tools that can support running workloads concurrently. Now, one thing we can consider is stream, as we have introduced in the fourth section. Stream has this property that if there are two tasks that are in the same stream, they will be guaranteed to execute in order, one after another. If two tasks are in two different streams, they are very likely to be able to execute concurrently. So we can use stream to control multiple GPUs. So the idea is to create a stream for each GPU. And as we insert the kernels into different streams, those streams map to different GPUs, and those kernels can be executed concurrently. So let's see one example directly. In the previous sections, we have seen this vector add program again and again, because it's very simple. So here, we'll continue to use this vector add example to demonstrate how to use multiple GPUs to process this vector add workload. At the beginning, we include some necessary header files, and we define this kernel. This kernel is nothing special. You should be already very familiar with this example. At the beginning of this program, we define a few variables. For example, we define the arrow, we define the device count, and we define the properties. And there are some workload-specific variables like length, the block size, and the number of GPUs that we want to use. Since I'm writing this program for my particular device, and I have 8 GPUs on my platform, then I just hard-code this number here. You can modify this number according to the platform that you have. Or you can use this getDeviceCount API to get the number of GPUs that are available. Next, we need to separate the task, which can be simply calculated with length divided by number of GPUs. And we also need to calculate the number of blocks that we're going to run on each GPU. In this part of code, we randomly initialize vector A and B. And here I want to call for attention. Previously, we defined this DA, DB, DC as regular float star, pointer to floating point numbers. But here, we're defining using an std vector, which is a list of buffers that are allocated on GPUs. If we have 8 GPUs, we have to have 8 DA, 8 DB, and 8 DC. And also, as we said, we want to create one stream for each GPU. And here, we're also creating a vector of streams. So to give you an overview of the structure of this program, I'm hiding the details here, but going to show you these 4 loops here. In the first loop, we create streams and allocate memory. Once the memories are ready, we launch the kernels in another loop. Finally, we synchronize. The synchronization cannot be in the same loop as kernel launching because we don't want the first GPU to run, then the second GPU runs. We want all the GPUs to run at the same time. So we launch the kernels. As kernel launchings are non-blocking, we launch all 8 kernels at once. Then we wait for all these 8 kernels to complete in this synchronization loop. Finally, we'll allocate some memory for the C buffer. Then we copy the data back from the GPU to the CPU. So let's look at the loop one by one. In the first loop, we first set a device. You will keep seeing this pattern that in the beginning of each iteration of the loop, we select the device that we want to use. So here we're selecting from 0 to 7. Then we create a stream. Since we set a device at the beginning, this particular stream that is created is associated with that particular device. Then we push back to the streams vector. We allocate some A pointer, B pointer, C pointer as some memory, and we push back to DA, DB, DC list. We perform memory copy for the input data. We copy the data from the CPU to the GPU side. If you want, you can also use the asynchronous version of heap memory copy. Now you can push everything into streams. But here, for the purpose of simplicity, I'm only going to overlap the kernel execution. So at this point, we should have all the memory that is being copied to the GPU side. Then we're free to set, as you can see here, in each iteration, we first set a particular device that we want to use. Then we launch a kernel. That kernel will be launched to that particular device. And we have to also associate the device with that particular stream. And these kernels will be executed. This vector add call will return without waiting for the kernel to complete. So while the first GPU is executing this kernel, the CPU can work on launching the second kernel to the second GPU. Now while the second GPU is running, then the CPU can work on launching the third kernel to the third GPU. Finally, we launch all the kernels to all the GPUs. Now assuming the GPU need to take a very long time to perform the vector add operation as the data size is huge, the for loop will terminate before any kernels can complete. Now here, we need to explicitly wait for the kernels to complete. Note here that we don't need to set the devices anymore because the streams are already associated with the devices. And anyway, we just need to wait for all the streams to clear up. Finally, in the last loop, we copy the data back to the CPU side. Still, we're using this structure. We start a loop with number GPUs iterations, and at the beginning of each iteration, we set a device, then we perform a memory copy, so that it is that particular GPU that performs this memory copy operation. So far you have seen the full example, and you have seen this pattern being used again and again. And the most important part is the combination of this kernel launching loop and stream synchronization loop. We need to use one loop to launch the kernel and use another loop to perform the synchronization. And you can also see this pattern being used in the future videos. So as a summary, we want to summarize the stream-based multi-GPU programming skills. So the key idea is to create one stream for each GPU. We want to enqueue the tasks to the streams in loops. We can enqueue many memory copy and kernel launching tasks to the streams. Then finally, we need another loop to synchronize all the streams to wait for all the GPUs to complete their execution. Then we can start to exchange memory. So these three steps should be completed in individual loops. And the first thing to do in each iteration of the loops is to call this heap-set-device API. The advantage of stream-based multi-GPU programming is that it is very simple. But as you can see, another problem is we need to synchronize very often, and it's a little bit annoying to write the synchronization code. So if we have a workload that do not require regular synchronization, and we can let each GPU to run at the different stages of the program, then we can consider some other approaches. So in the next video, we're going to solve this problem by introducing thread-based multi-GPU programming.